The inverse function theorem is one of the central results of differential topology. Its content is a precise formulation of the following. If the best linear approximation to a smooth map at a point is invertible, then the map itself is locally invertible near that point, and its local inverse is again smooth. We develop this result in two stages. First, for smooth maps between open subsets of Rn, where the proof is analytic and rests on the contraction mapping lemma. Then the coordinate-free formulation for smooth maps between smooth manifolds, deduced from the Euclidean case by passing through smooth charts. Before either proof, we fix notation and recall the two analytic tools on which both proofs depend. Throughout, n is a positive integer. We write Br of A for the open Euclidean ball of radius r greater than 0 centered at A in Rn. We write B bar r of A for its closed counterpart, the closed ball, which includes the boundary sphere. The Frobenius norm of an M by N matrix A with real entries Aij is the square root of the sum of all squared entries. This norm on matrices is compatible with the Euclidean norm on vectors. The norm of A applied to V is at most the Frobenius norm of A times the Euclidean norm of V. This bound will be used in every Lipschitz estimate that follows. For a smooth map F from an open subset U of Rn to Rm, we write df of A for the total derivative, also called the Jacobian, at the point A in U. It is characterized as the unique linear map satisfying the following limit condition. The difference between f of A plus h and f of A and df of A applied to h divided by the norm of h tends to 0 as h tends to 0. This is the standard definition of Fréchet differentiability. When f is smooth, df of A exists at every A in U and varies smoothly with A. In the case n equals m, df of A is represented by the n by n Jacobian matrix of partial derivatives, whose determinant measures whether the linearization at A is invertible. For smooth manifolds M and N and a smooth map F from M to N, we write df at P for the differential of F at the point P. This is a linear map from the tangent space TPM to the tangent space TF of Pn. In a coordinate chart, the differential is computed as the total derivative of the coordinate representation of F. The result is independent of the choice of chart because the transition maps are diffeomorphisms and the chain rule applies. The differential is therefore the intrinsic coordinate-free analog of the Jacobian matrix. The Lipschitz estimate for C1 functions is the tool that controls displacement from derivative data. It rests on the fundamental theorem of calculus applied to the derivative along a line segment, and that argument requires the domain to be convex. The Lipschitz estimate controls the displacement of f between 2 points in terms of the derivative and the distance between the points. Given an open set U in Rn and a C1 map f from U to Rm, the claim is that f is Lipschitz continuous on every compact convex subset K of U. The Lipschitz constant is the supremum of the Frobenius norm of the Jacobian over K, call it script L. Compactness of K guarantees this supremum is finite, since the norm of the Jacobian is continuous and K is compact. Convexity of K ensures that the line segment between any 2 points of K lies entirely within K, which is the geometric condition required by the fundamental theorem of calculus argument. The content of the estimate is that the norm of f of b minus f of a is at most script L times the norm of b minus a for all a and b in K. This estimate is the quantitative bridge from derivative control to displacement control. The proof uses convexity of K and the fundamental theorem of calculus. For a and b in K, the entire line segment a plus t times b minus a lies in K for t, ranging from 0 to 1. This is exactly the definition of convexity applied to the 2 points a and b. Now apply the fundamental theorem of calculus component-wise to the smooth function t maps to f of a plus t times b minus a. The difference f of b minus f of a then equals the integral from 0 to 1 of df evaluated at a plus t times b minus a applied to b minus a dt. This integral representation converts the displacement in the image into an average of Jacobian values along the segment in the domain. Taking norms and using the operator norm bound, the norm of a matrix A applied to a vector V is at most the Frobenius norm of A times the Euclidean norm of V. The norm of f of b minus f of a is at most the integral from 0 to 1 of the Frobenius norm of df at a plus t times b minus a times the norm of b minus a dt. Since the Frobenius norm of df is bounded by script L everywhere on K, this integral is at most script L times the norm of b minus a. The Lipschitz estimate follows. The supremum script L controls the entire displacement, not just an average Jacobian value. The estimate is sharp at the point where the Jacobian norm achieves its supremum. This pointwise worst-case control is what makes the estimate useful in the contraction mapping argument. We will need to know that H is contractive on the entire ball, not merely on average, and that requires the sup norm of dH to be bounded, not just the average norm. The domain of the Lipschitz estimate is a compact convex subset K of U. Compactness ensures the supremum of the Jacobian norm over K is finite. Convexity ensures every line segment between 2 points of K lies entirely within K, the geometric condition required for the fundamental theorem of calculus argument. The codomain is Rm, F maps into a Euclidean space of possibly different dimension. Fix 2 points A and B inside K. The line segment from A to B lies entirely within K by convexity. The fundamental theorem of calculus applied component-wise to the smooth function T maps to f of a plus T times B minus A gives the integral representation f of B minus f of A equals the integral from 0 to 1 of df at a plus T times B minus A applied to B minus A dt. This converts the image displacement into an average of Jacobian values along the segment. As the parameter T sweeps from 0 to 1, the point A plus T times B minus A traces the segment in the domain, and its image under f traces a curve in the codomain from f of A to f of B. The image curve is in general not a straight segment, f is nonlinear, but its length is controlled by the sup norm of df on K. The Jacobian norm varies along the segment. The shading shows a region where the norm of df is larger, the darker band. The Lipschitz constant script L is the supremum of this norm over all of K, not just over the segment. It is this worst case value that controls the displacement norm of f of B minus f of A. The estimate uses the supremum, not the average, because the integral of a function bounded by script L over an interval of length 1 is at most script L. The arrow from the peak of the Jacobian norm to the label script L identifies the controlling quantity. The Lipschitz bound norm of f of B minus f of A is at most script L times norm of B minus A, follows directly. Taking norms inside the integral and bounding the Jacobian norm by script L gives norm of f of B minus f of A, at most the integral of script L times norm of B minus A over the unit interval, which equals script L times norm of B minus A. Moving the segment to a region where the Jacobian norm is uniformly smaller produces a shorter image arc. The shading is now approximately uniform and dim. The Jacobian norm is close to constant and small on this segment. The new effective Lipschitz constant script L prime is strictly less than script L, and the image displacement is proportionally smaller. This demonstrates that the bound is sharp. Smaller Jacobian norm on K gives a smaller Lipschitz constant and a tighter displacement bound. A contraction on a metric space X with metric D is a self-map G of X for which there exists a constant lambda strictly between 0 and 1, such that D of G of X and G of Y is at most lambda times D of X and Y for all X and Y in X. The factor lambda is called the contraction constant. A fixed point of G is a point X satisfying G of X equals X. The condition lambda strictly less than 1 is essential. A non-expansive map, where the bound holds with lambda equal to 1, need not have a fixed point. A rigid rotation of the unit circle is non-expansive, but has no fixed point unless it is the identity. The strict contraction condition forces every pair of orbits to converge toward each other at a geometric rate, which is what makes existence and uniqueness of a fixed point provable. The contraction. Lemma asserts that on a non-empty complete metric space, every contraction has a unique fixed point. Completeness is the other essential hypothesis. It ensures that Cauchy sequences converge within X. If X has gaps, the orbit sequence constructed in the existence proof may converge to a point outside X, and the fixed point equation would then fail. This lemma will be the engine that produces a local inverse in the proof of the inverse function theorem. We will encode the problem of finding a pre-image of Y as a fixed point equation for a contraction on a closed ball, and the lemma delivers the required pre-image. The proof of the contraction. Lemma has two logically independent parts. Uniqueness is proved first because it is shorter and uses only the contraction inequality directly, without constructing any sequence. Existence requires an explicit construction, the orbit sequence, and uses completeness to pass from Cauchyness to convergence. Uniqueness. Suppose x and x prime are both fixed points of G. Then d of x and x prime equals d of g of x and g of x prime, since both are fixed. By the contraction property, this is at most lambda times d of x and x prime. Rearranging, 1 minus lambda times d of x and x prime is at most 0. Since lambda is strictly less than 1, the factor 1 minus lambda is strictly positive, and since d is a metric, it is non-negative. So d of x and x prime must be 0, hence x equals x prime. Uniqueness is established. Existence. Fix any x0 in X and define the orbit sequence by xn plus 1 equals g of xn by applying the contraction property n times d of xi, and xi plus 1 is at most lambda to the I times d of x0 and x1. To show the sequence is Cauchy, fix indices I less than or equal to j and use the triangle inequality. The distance d of xi and xj is at most the sum of d of xk and xk plus 1 for k running from I to j minus 1. Each term is at most lambda to the k times d of x0 and x1, and summing the geometric series gives lambda to the I over 1 minus lambda times d of x0 and x1, which tends to 0 as I tends to infinity. So the sequence is Cauchy. By completeness of x, the Cauchy sequence xn converges to some limit x in x. Continuity of G, which holds because any contraction is Lipschitz with constant lambda, hence uniformly continuous, gives G of x equals G of the limit of xn, which equals the limit of G of xn by sequential continuity, which equals the limit of xn plus 1, which equals x. So x is a fixed point. Uniqueness was proved above. Together, these two parts establish that every contraction on a complete metric space has exactly one fixed point. The orbit from any starting point converges to it. The proof is complete. What the lemma does not tell us is where the fixed point is, only that it exists and is unique. In the inverse function theorem, we will identify the fixed point as the preimage of a given y, and we will additionally show it lies inside a specified open ball. The complete metric space X is depicted as a disk. The unique fixed point X star, whose existence and uniqueness the contraction lemma asserts, is marked at the center. The lemma makes no assertion about where X star is. Placing it at the geometric center is a visual convenience to display convergence of orbits. Two orbits are initialized from opposite sides of X, starting points x0 and y0. The contraction constant lambda equals 0.6, meaning each application of G reduces distances by a factor of at least 0.6. Each iteration moves both orbits closer to X star. At each step, the distance d of xn and yn, the dashed segment, shrinks by the factor lambda equals 0.6, so after n steps it is lambda to the n times the initial distance. The geometric convergence rate, lambda to the n, tends to 0, which is what makes the orbit sequence Cauchy for large I. The tail distances are bounded by a geometric series sum whose total is lambda to the I over 1 minus lambda times the initial step. Both orbits converge to the same point X star. The distance d of xn and yn tends to 0, confirming that any two orbits under a contraction must converge to the same limit, uniqueness. The limit x star satisfies g of x star equals x star because g is continuous, and x star is the limit of the orbit g of xn, existence. The degenerate case lambda equals 1, a non-expansive map, is illustrated by a rotation on the unit disk. A rotation by an angle that is not a rational multiple of 2p preserves all distances. It is non-expansive with lambda equals 1, but has no fixed point. The orbit circulates indefinitely without converging. This is exactly why the contraction lemma requires lambda strictly less than 1, not merely lambda at most 1. The Euclidean inverse function theorem is the central analytical result of this presentation. The setup, U is an open subset of Rn, F is a smooth self-map of Rn defined on U, and the Jacobian matrix df of A is invertible at some point A in U. Invertibility here means the n by n Jacobian matrix at A has non-zero determinant. Equivalently, the columns of the Jacobian form a basis of Rn. The conclusion is that there exist connected open neighborhoods U0 around A inside U and V0 around F of A in Rn, such that the restriction of F to U0 is a diffeomorphism onto V0. That is, F restricted to U0 is bijective, smooth, and has a smooth inverse. The word connected is not vacuous. The argument produces neighborhoods that are balls or preimages of balls, and these are automatically connected in Rn. The hypothesis is purely on the linearization, not on F globally. F may be highly nonlinear, may fail to be globally injective, and may have complicated geometry far from A. Invertibility of the derivative at a single point is sufficient to guarantee local invertibility of the map itself with a smooth inverse. This is a purely local statement. The neighborhoods U0 and V0 may be very small, and the conclusion says nothing about F outside U0. The proof proceeds in 7 steps, 2 normalizing reductions that center the problem at the origin and make the derivative equal to the identity, a contraction estimate for the perturbation h of x equals x minus f of x, the surjectivity argument using the contraction lemma, an openness and connectedness argument for the domain and target neighborhoods, a differentiability proof for the local inverse, and finally a bootstrapped smoothness induction. The first two steps set up the framework that all subsequent steps use. The proof opens with two normalizing reductions. Each reduction replaces f with a map that satisfies an additional normalization condition that the distinguished point is the origin, and that the derivative at that origin is the identity. Both reductions are invertible. If the normalized map is a diffeomorphism near 0, then the original map f is a diffeomorphism near A, because the normalizing substitutions are themselves diffeomorphisms. Step 1. Translation. Set f1 of x equal to f of x plus a minus f of A. This translates the domain so the distinguished point is the origin, and translates the codomain so the image of the origin is the origin. The derivative df1 at 0 equals df of A. It suffices to prove the theorem for f1 at 0. Step 2. Normalize the derivative. Set f2 equal to df1 of 0 inverse composed with f1. Then f2 of 0 is 0, and df2 of 0 is the identity matrix In. If f2 is a diffeomorphism near 0, so is f1, and hence f. We rename f2 as f. From this point, the working assumption is f smooth near 0 with f of 0 equal to 0, and df of 0 equal to the identity. Step 3. The contraction estimate. Define the perturbation h of x equal to x minus f of x, then dh of 0 equals in minus in, which is the 0 matrix. Since the Jacobian of h depends continuously on x, f is smooth, so h is smooth, we can shrink the domain to a closed ball of radius delta centered at the origin, still inside U, such that the Frobenius norm of dh of x is at most 1/2 for all x in the closed ball. The threshold 1/2 is chosen because it is strictly less than 1. This is exactly what is needed to make h a contraction with constant 1/2, and to ensure the injectivity estimate norm of x prime minus x is at most 2 times norm of f of x prime minus f of x holds on the closed ball. Apply the Lipschitz estimate to h on this closed ball, which is compact and convex, and within U. The norm of h of x prime minus h of x is at most 1/2 times norm of x prime minus x for all x and x prime in the closed ball. From the contraction bound on h, we extract two consequences. Setting x prime equal to 0 in the Lipschitz bound gives the norm of h of x is at most 1/2 times the norm of x for x in the closed ball. Second, write x prime minus x as the sum of f of x prime minus f of x and h of x prime minus h of x. Taking norms, norm of x prime minus x is at most norm of f of x prime minus f of x plus norm of h of x prime minus h of x, which is at most norm of f of x prime minus f of x plus 1/2 norm of x prime minus x. Rearranging, 1/2 the norm of x prime minus x is at most the norm of f of x prime minus f of x. Therefore, f is injective on the closed ball of radius delta. If f of x equals f of x prime, then x equals x prime. These bounds, the Lipschitz contraction of h and the injectivity of f on the closed ball, are the inputs that step 4 will use to apply the contraction lemma for surjectivity. After the two normalizing reductions, we work with f smooth near 0, f of 0 equals 0, and df of 0 equals the identity In. The graph of f, shown in gold, is tangent to the diagonal y equals x at the origin, because df of 0 equals I means f is locally indistinguishable from the identity to first order. The perturbation h of x equals x minus f of x is drawn in red. Its derivative at 0 is dh of 0 equals I minus df of 0 equals I minus I equals 0. The graph of h is flat at the origin. Since h is smooth, its derivative varies continuously, so for x sufficiently close to 0, the derivative dh of x remains small. The closed ball of radius delta around the origin is shown in green. As delta shrinks, the maximum of the Jacobian norm of h over the ball decreases continuously because dh is 0 at 0 and continuous. By choosing delta small enough, the maximum of the norm of dh over the closed ball can be made at most 1/2. The Lipschitz estimate then bounds the norm of h of x prime minus h of x, which is at most 1/2 times the norm of x prime minus x for all x and x prime in the closed ball. This is the contraction bound on h with constant 1/2. Setting x prime equal to 0 in the contraction bound gives the norm of h of x is at most 1/2 times the norm of x for x in the ball. The dashed segment shows this bound since h of x is the vertical gap between the identity line and the graph of f, and that gap is controlled by half the distance from the origin. The injectivity estimate says that for 2 points x and x prime in the ball, the gap in the domain, norm of x prime minus x, shown on the horizontal axis, is at most twice the gap in the image, norm of f of x prime minus f of x, shown on the vertical axis. This means f cannot send two distinct points to the same image, and the distance between pre-images is controlled by the distance between images, the key bound used to prove continuity of f inverse in step 5. Step 4 establishes surjectivity. Fix E in the open ball of radius delta over 2 centered at 0. We need to find x in the open ball of radius delta with f of x equal to y. This is equivalent to finding a fixed point of the map G defined by g of x equals y plus h of x. We verify the two hypotheses of the contraction lemma for G on the closed ball of radius delta. First, G maps the closed ball to itself. For x in the closed ball, the norm of g of x is at most the norm of y plus the norm of h of x, which is at most delta over 2 plus 1/2 times delta, by the bound on y and the earlier estimate on h. This equals delta, confirming g of x lies in the closed ball. Second, g is a contraction. The norm of g of x minus g of x prime equals the norm of h of x minus h of x prime, which is at most 1/2 times the norm of x minus x prime, by the Lipschitz bound on h. The closed ball of radius delta is a complete metric space. It is a closed subset of Rn, which is complete, and closed subsets of complete metric spaces are complete. The contraction lemma provides a unique fixed point x in the closed ball, satisfying g of x equals x, hence f of x equals y. Moreover, from the estimate on g, the norm of x equals the norm of g of x is strictly less than delta over 2 plus delta over 2, which is strictly less than delta, so x actually lies in the open ball of radius delta. Since y was arbitrary in b delta over 2 of 0, every point of that open ball has a pre-image under f in the open ball of radius delta, which is precisely surjectivity of f from u0 onto v0. The Lipschitz estimate on f inverse, bounding the pullback distance by twice the image distance, comes next. Step 5. Continuity of f inverse. Set v0 equal to b delta over 2 of 0 and u0 equal to the intersection of b delta of 0 with the pre-image of v0 under f. u0 is open because it is the intersection of an open ball with the pre-image of an open set under a continuous map f. Steps 3 and 4 together show f restricts to a bijection from u0 to v0. From the injectivity estimate, norm of x prime minus x is at most twice the norm of f of x prime minus f of x. The inverse map satisfies norm of f inverse of y minus f inverse of y prime is at most 2 times norm of y minus y prime. So f inverse is Lipschitz continuous, hence continuous, and f is a homeomorphism from u0 to v0. u0 is connected because f is a homeomorphism from u0 to v0, and v0 equals b delta over 2 of 0 is convex, hence connected, and continuous bijections pull connected sets back to connected sets. With the homeomorphism and bijection established, the remaining question is whether the continuous inverse is differentiable, and that requires a separate argument using the defining property of the Jacobian of f. The surjectivity argument works with two concentric regions. On the domain side, the closed ball of radius delta, inside which f is injective and on which h is contractive with constant 1/2. On the codomain side, the open ball of radius delta over 2, the target region that f must hit surjectively. The ratio of the two radii, 1/2, is determined by the contraction constant of h, which is 1/2. The bound on g of x requires that the norm of y plus 1/2 times delta is at most delta. Fix an arbitrary point E in the inner ball of radius delta over 2. The surjectivity goal is to find a point x in the outer ball satisfying f of x equals y. This is equivalent to finding a fixed point of the map g of x equals y plus h of x, since g of x equals x means y plus h of x equals x means y plus x minus f of x equals x means f of x equals y. The orbit of G, starting at a point on the boundary of the outer ball, converges geometrically toward the fixed point x star of y inside the ball. G maps the closed ball to itself. For x in the closed ball, the norm of g of x is at most the norm of y plus 1/2 times the norm of x, which is at most delta over 2 plus delta over 2, which equals delta. G is contractive with constant 1/2 because g of x minus g of x prime equals h of x minus h of x prime, bounded by 1/2 times norm of x minus x prime. The contraction lemma on the complete space, the closed ball, delivers a unique fixed point. The fixed point x star of y, marked in green, satisfies f of x star of y equals y. The curved arrow from the domain to the codomain represents this. F sends x star of y to the target y. The fixed point lies strictly inside the open ball of radius delta, not merely on its boundary, because the norm of x star equals the norm of g of x star is strictly less than delta. As y traverses the inner ball, the corresponding fixed point x star of y moves continuously in the outer ball. This is because x star of y depends continuously on y. The fixed point equation g of x equals x, with g depending continuously on y, makes x star of y continuous in y by the uniform contraction bound. Since y ranges over all of b delta over 2 of 0, the preimages x star of y cover all the necessary points. F surjects onto the entire inner ball. For each y there is a unique such x star of y, giving both surjectivity and injectivity on u0 simultaneously. Step 6 establishes that F inverse is differentiable, not merely continuous. The strategy is to show that the difference quotient for F inverse at any y in V0 satisfies the definition of Frechet differentiability, with derivative equal to the inverse of df at the corresponding preimage. Fix y in V0 and set x equal to F inverse of y and L equal to df of x, the Jacobian of f at the preimage x. For y prime in V0 different from y, write x prime for F inverse of y prime. We must show that the difference quotient for F inverse, namely F inverse of y prime minus F inverse of y minus L inverse applied to y prime minus y, normalized by the norm of y prime minus y, tends to 0 as y prime tends to y. The key algebraic identity inserts y prime minus e equals f of x prime minus f of x into the numerator of the difference quotient for F inverse. After substituting and rearranging, the difference quotient splits into a product, the ratio norm of x prime minus x over norm of y prime minus y, which is bounded above by 2 from the injectivity estimate of step 3, times L inverse applied to the normalized remainder of f at x, namely f of x prime minus f of x minus L times x prime minus x divided by norm of x prime minus x. This split is the right one because each factor can be separately controlled as y prime tends to y. The ratio norm of x prime minus x over norm of y prime minus y is at most 2 by the injectivity estimate from step 3, a bounded factor. As y prime tends to y, continuity of F inverse, from step 5 gives x prime tending to x. The remainder term f of x prime minus f of x minus L times x prime minus x divided by norm of x prime minus x tends to 0 precisely because df of x is the derivative of f at x. That limit condition is the definition of Frechet differentiability of f at x. The product of a factor bounded by 2 and a factor tending to 0 tends to 0. Therefore f inverse is differentiable at y, with derivative df inverse of y equal to df of f inverse of y, all to the power minus 1. This formula expresses df inverse as a composition of 3 maps, f inverse, then df, then matrix inversion, each with its own regularity, and that factored structure is exactly what step 7 exploits. Step 7. F inverse is smooth, not merely differentiable. The formula df inverse of y equals df of f inverse of y, all to the minus 1, expresses the derivative of f inverse as the composition of 3 maps, f inverse itself from v0 to u0, then df, the Jacobian of f, mapping u0 to the general linear group gln of R, where gln of R denotes the open subset of the space of n by n matrices consisting of invertible matrices, then matrix inversion, the map sending the matrix A in gln to A inverse, mapping gln to itself. F inverse is continuous by step 5, df is smooth because f is smooth by hypothesis, and matrix inversion is smooth by Cramer's rule. Cramer's rule expresses A inverse as a rational function of the entries of A with non-zero denominator on gln, so it is smooth there. The composition of a continuous map and 2 smooth maps is C1, so the composition df inverse is C1, which means f inverse is C2. For the induction, suppose f inverse is ck. Then df inverse is the composition of f inverse, which is ck, df, which is smooth, hence ck, and matrix inversion, which is smooth, hence ck. The composition of ck maps is ck, so df inverse is ck, which means f inverse is ck plus 1. By induction on k, f inverse is ck for every k, hence smooth. This completes the proof of the Euclidean Inverse Function Theorem. the key consequence that a pointwise invertible linearization suffices for local invertibility with a smooth inverse now extends to smooth manifolds by passing through coordinate charts. The derivative formula df inverse of y equals df of f inverse of y, all to the -1, factors as a composition of maps between three spaces. V0 is the open codomain neighborhood where f inverse is defined. U0 is the open domain neighborhood. GLn of R is the general linear group, the open subset of n by n matrices with non-zero determinant. GLn of R is itself a smooth manifold, and the regularity of maps into it is well defined. The first factor is f inverse itself, mapping V0 to U0. At this stage, the base case of the induction, f inverse is C1, which was established in steps 5 and 6, continuous from step 5, differentiable with formula df inverse equals df of f inverse, all inverse, from step 6. The second factor is df, the Jacobian of f, mapping U0 into GLn of R. df is smooth because f is smooth by hypothesis. The components of df are the partial derivatives of f, which are smooth whenever f is smooth, so df is C infinity. The third factor is matrix inversion, the map sending the matrix A in GLn to A inverse. This is a self-map of GLn of R. By Cramer's rule, A inverse equals the adjugate of A divided by the determinant of A. Both the adjugate and the determinant are polynomial in the entries of A, and the determinant is non-zero on GLn, so A inverse is a rational function of the entries with non-zero denominator, a smooth map on GLn. The composition df inverse equals matrix inversion composed with df composed with f inverse maps V0 to GLn. At k equals 1, each factor has regularity. F inverse is C1, df is smooth, hence C1, and inversion is smooth, hence C1. A composition of C1 maps is C1, so df inverse is C1. A map whose derivative is C1 is itself C2. So f inverse is C2 at the end of the first inductive step, one class smoother than at the start. The induction continues so that at each stage k, f inverse is ck, so df inverse is a composition of three ck maps, ck, since the class ck is closed under composition, and a map with ck derivative is ck plus 1. The counter increments to 3, 4, 5, and beyond. Since k is arbitrary, f inverse is ck for every finite k, hence smooth. Two corollaries follow immediately from the Euclidean Inverse Function Theorem. The hypothesis for both is that U is open in Rn, f is smooth on U, and the Jacobian determinant of f is non-zero at every point of U, that is, df of x is invertible throughout U. First conclusion, f is an open map. Every open subset U prime of U has open image. Second conclusion, if f is additionally injective on all of U, then f is a diffeomorphism from U onto its image. Part A extends the local result. Each point has a local diffeomorphism neighborhood to a global statement about open sets by covering. Part B strengthens the conclusion from local to global diffeomorphism when injectivity is assumed as an additional hypothesis. The proofs are short applications of the theorem. For the open mapping property, at each point A in U prime, invertibility of df of A allows the inverse function theorem to supply an open neighborhood VA of f of A that is entirely contained in f of U prime, because the IFT produces a local diffeomorphism from a neighborhood of A onto VA, and that neighborhood lies inside U prime. Every point of f of U prime therefore has an open neighborhood inside f of U prime, so f of U prime is open. For the diffeomorphism conclusion, if f is globally injective, its set theoretic inverse f inverse exists on f of U as a function. Near each point f of A in f of U, the restriction of f to a local neighborhood of A is a diffeomorphism onto a neighborhood of f of A by the IFT. F inverse on that neighborhood coincides with the smooth local inverse from the IFT, so f inverse is smooth near f of A. Since f of A was arbitrary, f inverse is smooth on f of U. With both f and f inverse, smooth and f bijective, f is a diffeomorphism from U to f of U. These two corollaries are the Euclidean consequences. The manifold versions follow once we transport the theorem through coordinate charts. A smooth map f between smooth manifolds. M and N is called a local diffeomorphism if every point P in M has an open neighborhood, U, such that f of U is open in N and f restricted to U is a diffeomorphism onto f of U. This is a pointwise condition about local invertibility. The neighborhood U may vary with P, and the condition asserts nothing about f outside U. A local diffeomorphism need not be globally injective or surjective. The exponential map from R to the circle is a local diffeomorphism that wraps the line around the circle infinitely many times. The manifold inverse function theorem will characterize local diffeomorphisms precisely as smooth maps with everywhere invertible differentials, the condition that must hold at each point P separately. The manifold version of the inverse function theorem replaces the Jacobian invertibility condition with the coordinate-free condition that the differential df at P, a linear map from Tpm to Tf of Pn, is a linear isomorphism. Both M and N are required to be smooth manifolds without boundary. The necessity of this hypothesis on the domain is explained in the next section. The conclusion is identical in structure to the Euclidean case. Connected open neighborhoods U0 of P and V0 of F of P exist such that F restricted to U0 is a diffeomorphism onto V0. F is therefore a local diffeomorphism at P. The proof reduces this to the Euclidean case by choosing smooth coordinate charts centered at P and F of P and applying the Euclidean theorem to the coordinate representation of F. The proof reduces the manifold statement to the Euclidean theorem in 4 steps: a dimension argument, a coordinate representation, application of the Euclidean theorem to the coordinate form, and lifting the Euclidean conclusion back to the manifolds. No new analytic content is needed beyond what was established for the Euclidean case. The work here is entirely about translating between the manifold and Euclidean settings via smooth charts. Dimension equality. Since df at P is a linear isomorphism between the finite dimensional tangent spaces Tpm and Tf of Pn, these spaces must have the same dimension. A linear isomorphism between finite dimensional vector spaces is possible only when the dimensions are equal. Therefore, the dimension of M equals the dimension of N, call it N. This is the same equidimensionality that the Euclidean inverse function theorem requires. Coordinate representation. Choose smooth charts, a chart U and phi for M centered at P, meaning phi of P equals 0, and a chart V and psi for N centered at F of P, meaning psi of F of P equals 0, with F of U contained in V. The coordinate representation is the composition psi of F composed with phi inverse, a smooth map from the open subset phi of U in Rn to the open subset psi of V in Rn, sending 0 to 0. By the chain rule for differentials, the total derivative df tilde of 0 equals d psi at F of P composed with df at P composed with the differential of phi inverse at 0. Each of these 3 factors is a linear isomorphism df at P by hypothesis and d psi at F of P and the differential of phi inverse because coordinate charts are diffeomorphisms and the differentials of diffeomorphisms are linear isomorphisms. A composition of linear isomorphisms is a linear isomorphism, so df tilde of 0 is an invertible n by n matrix. Apply the Euclidean inverse function theorem to f tilde at 0. Since df tilde of 0 is invertible, the theorem supplies connected open sets u tilde 0 and v tilde 0 in Rn, both containing 0, such that f tilde restricted to u tilde 0 is a diffeomorphism onto v tilde 0. The theorem is applicable because f tilde is a smooth map between open subsets of Rn and its Jacobian at 0 is invertible, exactly the Euclidean hypotheses. Lift back to M and N. Set u0 equal to phi inverse of u tilde 0 and v0 equal to psi inverse of v tilde 0. These are connected open neighborhoods of P and F of P respectively, open because phi and psi are homeomorphisms, and connected because u tilde 0 and v tilde 0 are connected and homeomorphisms preserve connectedness. The restriction of f to u0 equals psi inverse, composed with f tilde restricted to u tilde 0, composed with phi. This is a composition of 3 diffeomorphisms. Phi is a diffeomorphism from u0 to u tilde 0, f tilde restricted to u tilde 0 is a diffeomorphism onto v tilde 0 by the Euclidean theorem, and psi inverse is a diffeomorphism from v tilde 0 to v0. A composition of diffeomorphisms is a diffeomorphism, so f restricted to u0 is a diffeomorphism onto v0. The proof is complete. The boundary hypothesis on the domain will be examined next. The smooth map F between the manifolds M and N is drawn at the manifold level. M and N are depicted as irregular blobs, not flat, to indicate they are curved manifolds without preferred coordinate systems. The point P in M and its image F of P in N are marked. The differential df at P is a linear isomorphism by hypothesis. The proof must produce local diffeomorphism neighborhoods from this. Smooth coordinate charts phi and psi descend from the manifold level to the Euclidean level. The chart phi maps a neighborhood U of P in M diffeomorphically onto the open disk phi of U in Rn, with phi of P equal to 0. The chart psi maps a neighborhood V of F of P in N diffeomorphically onto psi of V in Rn, with psi of F of P equal to 0. Both phi and psi are diffeomorphisms, so their differentials are linear isomorphisms. The coordinate representation F tilde equals psi composed with F composed with phi inverse is a smooth map from phi of U to psi of V, both open subsets of Rn, and it sends 0 to 0. F tilde is the Euclidean form of F in these coordinates, and it is smooth because F, phi, and psi are all smooth. The chain rule expresses df tilde at 0 as the composition of three differentials, the differential of phi inverse at 0, which is the inverse of d phi at P, hence a linear isomorphism, then df at P, a linear isomorphism by hypothesis, then d psi at F of P, a linear isomorphism because psi is a diffeomorphism. A composition of three linear isomorphisms is a linear isomorphism, so df tilde of 0 is an invertible n by n matrix. The invertibility of df at P is equivalent to the invertibility of df tilde at 0, and the Euclidean inverse function theorem applies to f tilde. The Euclidean inverse function theorem delivers connected open subsets, u tilde 0 and v tilde 0 of Rn, both containing 0, such that f tilde restricted to u tilde 0 is a diffeomorphism onto v tilde 0. These are the Euclidean level neighborhoods produced by the analytic theorem. Applying phi inverse and psi inverse lifts the Euclidean conclusion back to M and N. U0 equals phi inverse of u tilde 0 is a connected open neighborhood of P in M, open and connected because phi is a homeomorphism and u tilde 0 is open and connected. V0 equals psi inverse of v tilde 0 is a connected open neighborhood of F of P in N. The restriction of F to U0 equals psi inverse composed with F tilde on U tilde 0 composed with phi, a composition of diffeomorphisms, hence a diffeomorphism. The manifold inverse function theorem is proved. The hypothesis that the domain M has empty boundary is essential and cannot be dropped. A smooth map whose domain is a manifold with boundary can fail to be a local diffeomorphism at a boundary point even when its differential there is invertible. The obstruction is geometric. A neighborhood of a boundary point in M is modeled on the upper half space Hn, the closed half space Xn greater than or equal to 0 in Rn, not on a full open ball. A diffeomorphism from a manifold with boundary to a manifold without boundary would require a homeomorphism between a half space neighborhood and a full open ball. No such homeomorphism exists. A half space has a boundary, the hyperplane Xn equals 0, while an open ball does not, and boundary points are topologically distinguished from interior points. Therefore, the Euclidean inverse function theorem, which applies to fully open subsets of Rn, does not extend to boundary points of M. The situation for the codomain N is different. If N has non-empty boundary but the differential df at P is a linear isomorphism, then F must map a neighborhood of P into the interior of N. The reason, df at P being an isomorphism, forces the local degree of F to be +1 or -1, which is inconsistent with the image landing on the boundary of N. The boundary is a codimension 1 submanifold and would force a rank drop in the differential. The interior of N is a smooth manifold without boundary, so the theorem applies with N replaced by its interior, and the conclusion holds with V0 inside the interior. A manifold with boundary has a topological boundary, the locus at which the manifold with boundary is locally modeled on the upper half space Hn, the closed half space where the last coordinate is non-neg. A neighborhood of a boundary point P is homeomorphic to a half ball, an open ball intersected with the upper half space, not to a full open ball. The boundary line, marked in red, separates the interior of M from the boundary. A local diffeomorphism at P would require a homeomorphism from the half-disk neighborhood of P to a full open disk. No such homeomorphism exists. A half-disk has a topological boundary, the diameter, while an open disk has none. The boundary of a topological space is a topological invariant preserved by any homeomorphism. Therefore, the half-disk is not homeomorphic to a disk, and no local diffeomorphism at a boundary point can exist, even when the differential there is invertible. At an interior point Q of M, the local model is a full open ball. A neighborhood of Q is homeomorphic to an open disk in Rn. The Euclidean inverse function theorem applies. It requires an open neighborhood, and the interior of M provides exactly that. At interior points with invertible differential, a local diffeomorphism neighborhood exists. When the codomain N has non-empty boundary, the situation is different. If df at P is a linear isomorphism, then f of P cannot lie on the boundary of N. if f of p were on the boundary of n, a local neighborhood of f of p in n would be a half ball, and the image of a local diffeomorphism on a full ball neighborhood of p cannot be a half ball. A full ball neighborhood maps onto a full ball neighborhood. This forces f of p to lie in the interior of n. The interior of n is a smooth manifold without boundary, so the manifold inverse function theorem applies with n replaced by int of n. A smooth map F between smooth manifolds without boundary is a local diffeomorphism if and only if it is simultaneously an immersion and a submersion. F is an immersion. If the differential df at P is injective at every P in M, this requires the dimension of M to be at most the dimension of N. F is a submersion. If df at P is surjective at every P in M, this requires the dimension of M to be at least the dimension of N. The combined condition is therefore that df at P is both injective and surjective at every point of M. That is, df at P is a linear isomorphism at every P, which is exactly the pointwise hypothesis of the manifold inverse function theorem. When the dimensions of M and N are equal, a linear map between spaces of equal finite dimension is injective if and only if it is surjective. This is the rank nullity theorem applied to an endomorphism of a finite dimensional space. So, in the equidimensional case, either rank condition alone implies full rank, and either hypothesis implies the other. The proof of part A. The forward direction. If f is a local diffeomorphism, then at every p the differential df at P is a linear isomorphism, hence injective and surjective separately. The backward direction. If f is both an immersion and a submersion, df at P is bijective, both injective and surjective, at every p, hence a linear isomorphism, and the manifold inverse function theorem gives a local diffeomorphism at each point. Part B, when the dimension of M equals the dimension of N equals N, the tangent spaces Tpm and Tf of Pn both have dimension n. A linear map between two n-dimensional spaces is injective if and only if it is bijective. Injectivity forces the image to be a subspace of dimension n, which is the full space, and similarly for surjectivity. Therefore, any linear endomorphism of Rn that is either injective or surjective is automatically a linear isomorphism, so either rank condition implies full rank and part A applies. The corollary states that bijectivity and local diffeomorphism together imply global diffeomorphism. If f is bijective and a local diffeomorphism, the set theoretic inverse f inverse exists on n as a function. At each point q equals f of P in n, the manifold inverse function theorem supplies an open neighborhood W of P and a smooth diffeomorphism from W to f of W. On W, f inverse coincides with this smooth local inverse, so f inverse is smooth near Q. Since Q was arbitrary in N, f inverse is smooth on N. With f smooth, f inverse smooth, and f bijective, f is a diffeomorphism from M to N. No additional hypothesis beyond bijectivity is needed. The local structure provided by local diffeomorphism is enough to promote bijectivity to global smoothness of the inverse. The rank of the differential df at P determines the type of the smooth map. A tall matrix, more rows than columns, represents the Jacobian of an immersion. The dimension of M is less than the dimension of N, and the differential has rank equal to the dimension of M, full column rank, hence injective. A square matrix of full rank, the dimension of M equals the dimension of N, represents a local diffeomorphism. The differential is square and invertible. A wide matrix, more columns than rows, represents a submersion. The dimension of M is greater than the dimension of N, and the differential has rank equal to the dimension of N, full row rank, hence surjective. The square case is the conjunction of immersion and submersion. The differential is both injective and surjective, hence bijective. A bijective linear map is a linear isomorphism, the hypothesis of the manifold inverse function theorem at each point, so the map is a local diffeomorphism. Forward direction. A local diffeomorphism implies both immersion and submersion. If df at P is an isomorphism at every P, it is injective at every P, so f is an immersion, and surjective at every P, so f is a submersion. The arrows from the local diffeomorphism label to the immersion and submersion labels represent this implication. Backward direction. Immersion plus submersion implies local diffeomorphism by the manifold inverse function theorem. If df at P is injective and surjective at every P, it is a linear isomorphism at every P, and the manifold inverse function theorem applies pointwise, producing a local diffeomorphism neighborhood at each P. In the equidimensional case, the dimension of M equals the dimension of N equals N. A linear map from Rn to Rn is injective if and only if it is surjective. This is a consequence of the rank nullity theorem for a square matrix. Rank plus nullity equals n, so rank equals n if and only if nullity equals 0 if and only if the map is injective, and rank equals n if and only if the image is all of Rn, if and only if the map is surjective. The double-headed arrow shows this equivalence, that for n by n matrices, injectivity and surjectivity are equivalent, so either rank condition alone implies the other and implies local diffeomorphism. The failure case for part B, when the dimension of M is strictly less than the dimension of n, an injective linear map from Rm to Rn with m less than n cannot be surjective. Its image is an m-dimensional subspace of Rn, which has dimension strictly less than n, so an immersion with the dimension of m strictly less than the dimension of n is never a submersion, and the equidimensional hypothesis in part B cannot be dropped. The tall matrix has rank equal to the dimension of m equals 2, full column rank, hence injective, but rank 2 is less than the dimension of n equals 3, so it fails to be surjective and fails to be a local diffeomorphism. The logical structure of this presentation is a strictly linear chain of implications. The Lipschitz estimate, proved via the fundamental theorem of calculus applied to the derivative along line segments in a compact convex set, supplies the contraction bound on h of x equals x minus f of x. That contraction bound is the hypothesis of the contraction lemma, which delivers existence and uniqueness of the fixed point that serves as the local preimage. The contraction lemma therefore implies the Euclidean inverse function theorem. The Euclidean theorem, transported through coordinate charts via the chain rule, implies the manifold inverse function theorem. The manifold theorem implies the corollaries on open mappings, diffeomorphisms, immersions, submersions, and local diffeomorphisms. The single mechanism underlying the entire argument is the propagation of linear algebraic invertibility to nonlinear local invertibility. The differential df at P, or the Jacobian df of A, is the best linear approximation to f near P. When that linear approximation is invertible, a fixed point argument constructs a local inverse to f, and a bootstrapped smoothness induction proves the local inverse is as smooth as f. This propagation is coordinate independent, it holds in any smooth coordinate chart and therefore on any smooth manifold, as the manifold proof makes explicit. The Jacobian or differential is the complete local model of the map at a single point, and invertibility of that model at one point is sufficient and necessary for local invertibility of the full nonlinear map.